Hello, general chemistry students. I want to help you think through a acid-base titration. This one is with a strong base, barium hydroxide. You have that in a flask, and then dripping in hydrochloric acid. This is one of the OWL problems that we had. So it's laid out here. You can see it says 80 milliliters, the concentration of barium hydroxide, and then we're adding in hydrochloric acid. Calculate the pH after the following volumes of HCl have been added. And so that's sort of the key there that we know, because this is adding HCl. Now, the important thing to remember is setting up the chemical reactions. And so here's the problem laid out in OWL. We got to think of barium hydroxide as it is a strong hydroxide, and so we're going to think of it as the OH minus. That's our reactant. And so we'll think of it as our first one. That's our base. But remember, for every 1 barium hydroxide, 2 moles of barium hydroxide are given off. Now, barium is a neutral cation, so we can ignore it. HCl, chloride, is a neutral ion. We'll ignore it. And reacts with water to make the hydronium ion, because it transfers the proton to the water. So anytime you have a strong acid, HCl, HBr, HI, we always think of it and we write it down as H3O+. So the reaction then is hydroxide plus the hydronium ion, and the only thing it makes there is water. In fact, it makes 2 moles of water. So this is a strong reaction. It goes 100% to the right, and you're going to run any of these calculations in moles first. So we called this like the BRF table, before, reactant, and final. So let's look at the first one. Now, in the first one, there is no HCl, so you don't run that reaction. All we have to do is calculate the concentration of hydroxide and get the POH. Now, I did that by just doubling the concentration given, because the concentration given is for barium hydroxide. There's 2 moles of hydroxide, so we just double it, take the minus log, and that will give you the POH. Subtract from 14, and we get the pH. So the first situation is just 13.3 for the pH. So it's up high. It's a very high concentration of hydroxide. Look at the second one. Now in the second one, now we're going to run the reaction between hydroxide and the hydronium ion. Let's get the hydroxide ion. Let's do it in millimoles. It's really good to do it in that. All you do is take the volume in milliliters times the concentration, but I have to double it because of the 2 hydroxides. 16 millimolar hydroxide. 20 mils of HCl times its concentration gives you 8 millimoles. But remember, it's not HCl anymore. It's hydronium ions, because it's a strong acid. As soon as the strong acid hits water, it's hydronium. So I'm going to set up a BRF table to help think it through. Put the 2 reactant moles in there. And then I'm going to react, which means remove the least reactant, so the limiting. So that's 8 millimoles of the hydronium ion. So the hydronium ion's gone. I have 8 millimoles of the hydroxide. Well, in order to figure out the POH, I need the hydroxide ion concentration. But since I'm adding 2 volumes in there, I've got to account for the increase in volume. 20 mils of hydrochloric acid and 80 mils of the barium hydroxide. 100 mils altogether. So I'm going to divide by that, and when I do that, I get 0.08 molar. Plug that into the minus log, get the POH 1.1, subtract from pH 12.9. All right, so you just repeat that for these other calculations at 30 and 40 milliliters. So I do that, showing that here you get the moles, and the moles of HCl is increasing. Just run it right back through a BRF table and divide it by the new volume. The volume is changing, so you got to account for that. Plug it in the POH and get your POH and pH. So it didn't drop a whole lot. And so now we get to the 40 mils, and I think you'll see at this point we actually have equal moles. So this is the equivalence point, where you have equal moles of both reactants. And when you look at that reaction, there is none of the strong base, none of the strong acid left. You have nothing but water. So you go and figure out the pH. I'll show you on the next slide, or 2. Okay, what's the pH of this pure water that's available? You should know this. All right, and the last calculation may be a little different, but calculate the same thing, moles of both. But now I have more moles of the hydronium ion. So I react the 16 millimoles of the base, and that wipes out all but 4 moles of the acid. So now all I have is hydronium ion. And I divide it by the new total volume, which is 130 milliliters, 80 plus 50, and I get the concentration. But now the concentration is hydronium ion, and I can go right into pH and figure that out, 1.51. Now, the problem didn't ask you to do this, but I'm going to take the opportunity to show you what the titration curve looks like. And when you plot the points at 0 HCl added, 20 milliliters added, okay, 12.9, 30 milliliters added, pH, when you add 40 mils of HCl, that's the equivalence point. It's neutral at 7. And after adding 10 more mils of hydrochloric acid, this is what the titration curve looks like. Now, the end point where we would stop the chemical reaction is at the 40. That's when in the lab we would stop. But it can be helpful, and scientists do continue the titration because there's a way mathematically to figure out that end point if you go past it. We won't do that in lab, but scientists go past the end point. The halfway point is just half the volume, half the moles of the equivalence point. So that's the titration between a strong base and a strong acid. Notice the shape, how kind of flat it is at the top. And then boom, it drops down a lot of pH points because you're adding an acid. And halfway point is at 7. Or not the halfway point. The equivalence point is at 7. That's for any strong base, strong acid titration. It doesn't matter the order, doesn't matter if it's strong acid, strong base, always neutralizes to water. Hope you found that video helpful and that you can put into practice these things that you've learned.